Here we're going to calculate energy transferred in a chemical reaction using bond energies. So the idea is, behind all this, whenever you have a reaction, you can work out the overall energy change by looking at the energies in each bond. So the first thing you have to do whenever you've got a reaction, say I've got this H2 and Cl2, and they form HCl and HCl, it's balanced. The first thing I'll have to do for these to be able to react is I will have to break this bond here between the H's, and I'll have to break this bond here between the chlorines. So if I don't do that, I can't form these new compounds. So step one, whenever you have a reaction, you need to break bonds. And then once you've broken those bonds between the hydrogens and the chlorines, you can then form bonds. So step two is then to form bonds. And overall, you'll have some energy associated with this whole reaction. Now, to break bonds, this requires energy to do. So energy has to go into the system. Okay, so this requires energy in. And when you form bonds, this often releases energy. So to break bonds, this requires energy to go into the system. When you form bonds, energy is released. So bond energy calculations associate really closely to this idea of exothermic and endothermic. So just looking at the words, well, exo kind of means outside. So we've got out, and endo means inside or within. So that's in. And the idea of thermic, well, that's to do with heat. So very simply, exothermic means heat's given out, and endothermic means heat's taken in. Now these are really simple ways to look at it, and actually it's not a very good way to explain it, so let's explain it in a bit more detail, but that's just a way of remembering them. So when we say heat is given out, what we actually mean is that energy is released. So when you have a reaction, energy is released from the reaction. So this is why it will often feel hot. When we say it's endothermic and heat's taken in, well, what we mean here is actually that energy is taken in from surroundings. And this is energy released to surroundings. So exothermic will often feel hot because energy is released. Endothermic, it will often feel cold because energy is taken in. Now going back to what we said on the previous slide, was that to form bonds, energy is released. So that links to the exothermic bit. So for the exothermic bit, this is to do with forming bonds. And the endothermic is where energy is taken in. Well, we said energy needs to be taken in to break the bonds. So we have break bonds. Now, of course, in any reaction, we have to do both. We have to break the bonds first of the reactants and then form the bonds of the products. So overall, if the reaction is exothermic, it just means the energy released forming bonds is greater than the energy taken in breaking bonds. So let's write that up now. So if exothermic reaction overall, it means that the energy released forming bonds is greater than the energy taken in to break bonds. And the opposite, if it's endothermic overall, it means that the energy taken in to break the bonds in the first place is greater than the energy released forming bonds. So now what we're going to do some calculations based around these ideas to try and give you an example of what it's all about. So let's read through this question. So it says combustion is an exothermic reaction. Calculate, so I'm going to have to use some maths here, the overall energy change for the complete combustion of 1 mole of methane and oxygen. So it's given me the formula here, and it's shown me all the bonds that are in it as well. Show me it's 3 marks. It's given me the unit, so the units match up, so I'm happy with that. Now let's just go through making sure we understand what all this means. It says it's exothermic, so this means I've got energy released overall. And if energy is released overall, then my overall energy change is negative. So my answer is going to have to be a negative number. I'm happy with what the word calculate means. The overall energy change. So overall energy change equals, it'll be the sum of all bonds broken. So I add up all the bonds that I have to break and then take away the sum of all the bonds formed. So as long as I do that, I should get my overall energy change, and I know it's exothermic, so I know my answer should be negative. So first thing I have to do to make this reaction happen is I need to break the bonds of the reactants and then form the bonds of the products. So I'll have to break this bond, this bond, this bond, and this bond. So that means I have to break 4 lots of CH bonds. Now it says here that the CH bond is 413 kilojoules per mole. So I've got 4 lots of 413 and add that to the bonds I'm going to break here. So I'm going to break this oxygen-oxygen bond, which is 498 kilojoules per mole, but I've got 2 of them because I've got 2 molecules of this, so I have to break both molecules. So I've got 2, 4, 9, 8. Okay, and they're the bonds that I'm going to break. So once I've broken them, I can then form my bonds. So breaking is 4 lots of 413, add it to 2 lots of 498. Okay, so that's my breaking, and my forming. I need to form that carbon-oxygen bond, and I need to form that carbon-oxygen bond. So that's 2 carbon-oxygen bonds I need to form. So that would be these. So I need to form 2 of them. I need to add it to, well, I've got a hydrogen-oxygen there and a hydrogen-oxygen there. So there's 2 hydrogen-oxygens, but I've got 2 of them in total. So I've got another molecule. So therefore I've got to form 4 bonds of those hydrogen-oxygens. Okay, so I know my hydrogen-oxygen is there. So then I've got 4 lots of 4, 6, 4. So that's my breaking. My forming is this. Now, the overall energy change is breaking minus forming, like I've shown you up here. The sum of the bonds broken minus the sum of the bonds formed. So the calculation here, 4 times 413 is 1652, and add that to 2 lots of that, that's this, equals 2648. And my forming is, if I do this calculation, that's that, add this, which equals 3466. So I've got my total for the bonds broken, bond energy, and I've got my total for the bonds formed. So the overall energy change is the total of the bonds broken minus the total of the bonds formed, which equals 818 kilojoules per mole. Sorry, negative. Now, what I like about this is that I know it tells me right at the start it's exothermic. If the reaction's exothermic, my overall energy change is negative, and you can see I've got a negative answer, so I'm reasonably happy with that. Now this question's slightly different, but it's based on all the same ideas. So pause it now, have a go yourself, or pause it halfway through after we've gone through some of the explanation about what you have to do, and really give it a go. So reading through the question, I've got the bond enthalpies and the overall change shown in table 6. Oh, so now it's given me the overall change, whereas it didn't last time. And this time it says I have to calculate the bond energy for the bromine-bromine bond, whereas last time I had all the bond energies. So you're doing the same equation, the same work, but you're just doing it slightly differently. So write out what we know. Well, we know that the sum of the bonds broken minus the sum of the bonds formed equals the overall energy change. So once you know that, maybe you can give it a go. If not, when you think you can give it a go, give it a pause. So I'm going to start off with bonds broken. So I have got one carbon-carbon double bond, so 612, and I've got 4 of those, 4 carbon hydrogens. So I've got 4 of those. I had 4 lots of 412, and they're the bonds broken for the ethene. And then I need to break the bond for the bromine-bromine, but I don't know it. So this is where I need to calculate it. So add my thing that I'm trying to work out. Now on the other side, I've got bonds formed. So I have got one carbon-carbon bond, so that's 348. And I've got 2 carbon-bromine bonds, so that's 2 lots of 276, and I have got 1, 2, 3, 4 lots of the carbon-hydrogen bond. And notice how I've ticked off the bonds as I go, so I know I've covered everything. So let's get totals for these now. So my total bonds formed, if I add all that together, is 2,548 kilojoules per mole. I also know that my bonds broken is 612, add 4 lots of this, add the thing that I'm trying to work out, my bromine-bromine bond. Now if I take this away, take away my bonds formed, I get the overall answer. Now my overall from the question is minus 95. So hopefully now you can try and give it a go and working out the bromine-bromine. To do this mathematically, I could rearrange it. So I've got my bromine-bromine bond, keep it on this side of the equals, and move everything to the other side. So I've got my minus 95. If I want to move minus 2,548, I need to add it to both sides. So add that, take away this, take away this, and doing that calculation, I'll get my answer of 193 kilojoules per mole. Is this sensible? Well, it's in the same ballpark as all the others, so yeah, I'm happy with that. Okay, so this is an absolutely fabulous question. It's a 6 marker, so it'll be right towards the end of your exam, probably the last question you're going to take on. Give it a go by working through it, really thinking about the process of how you're working through this. So the first thing we're going to do is we're going to read the question really carefully and unpack it. So it shows the reaction between ethene and chlorine similar to the reaction we've just done. So we've just done a reaction with ethene and bromine. They've shown us the formulas, the models for the reaction, and they've given us this statement. So the more energy levels, or the more shells of electrons an atom has, the weaker the covalent bond that it forms. So it says, use the above statement to predict and explain how the overall energy change for the reaction of ethene and chlorine will differ from the overall energy change for the reaction with ethene and bromine. Notice it's 6 marks, so it's going to take quite a bit of explanation. Now, the first thing I want to point out is this statement here. It says, use the above statement. So if the question tells you to use something, use it. Okay? If the question tells you to use a diagram, if the question tells you to use a table, use it. If you don't use it, you're not going to be able to access the marks. Now, I'm not sure where on earth to start with this, so I'm going to do what I always do when I get a bit stuck, and that's draw the electron configuration. So the thing that's different about these two, what's this asking me to look at, is the difference between the chlorine and the bromine. So I'm going to go to group 7 and I'm going to draw the electron configuration for chlorine, and I'm going to draw the electron configuration for bromine. Now, whenever you get stuck on something that's to do with reactions or bonding, draw the electrons and it'll help you out. I've only drawn the outer shell. I know they're all in group 7. So now I've drawn that, I'm going to try and use the statement that it's told me. So it says the more energy levels or shells, okay, I know bromine has got more shells, I can see that, the weaker the covalent bond. So if this has more shells, it's got a weaker covalent bond. Now, I've got this word covalent bond. Well, what's covalent bond? When is it a covalent bond? Covalent bonds happen between a non-metal and a non-metal. So these group 7 are all the non-metal. So if I bond either of these to another non-metal, it's a covalent bond. Covalent bonds are where they share a pair of electrons. So I'm going to start putting some statements about what I know. So I know chlorine atoms have fewer energy levels or shells. Okay, I've done that because I've drawn it, so I can see that. Based on the statement, I also know because they've got fewer energy levels, chlorine atoms form stronger covalent bonds than bromine atoms. Okay, so they're the statements I've made. I haven't actually used any of my knowledge yet at all. All I've done is drawn the electron configurations, and I've used the statement. I haven't had to think about anything. I haven't used any of my memory. I haven't used any revision. I'm just working step by step through this process. So the next step is to look at which covalent bonds the chlorine makes. So I know I can see that there's a chlorine-chlorine bond there. So I've got the chlorine-chlorine bond. If it makes a stronger bond, so the chlorine-chlorine will be stronger than the previous bromine-bromine bond. And I actually missed the second one first time, but there's also another covalent bond with the chlorines and the bromines, and there. So if chlorine makes stronger bonds, so the carbon-chlorine bond is stronger than the carbon-bromine bond. So again, I've not used any knowledge, I've just used a statement, the electron configurations to get to this point here. Next point, it's talking about overall energy changes. So I know the overall energy change is equal to the bonds broken minus the bonds formed. So if I'm trying to break the chlorine-chlorine bond, well, this is going to require more energy to break because it's stronger. However, my carbon-chlorine bond is also stronger. So this is going to release more energy when formed. So to break the chlorine-chlorine bond requires more energy because it's stronger, but I'll also in return get more energy released. So I can't exactly say what's going to happen because I need the exact numbers to be able to understand if it requires more to break them or form them. So my overall energy change depends on the size of the energy changes and how different it is for chlorine and bromine. But ultimately, we don't know this. So in order to predict what's going to happen, which is what it asks us to do, we have to make some assumptions. So if the carbon-chlorine bond changes less than the chlorine-chlorine bond, so it requires more energy to break the chlorine-chlorine bond. I'm spending more energy breaking the reaction will be less exothermic. Finally, if the carbon-chlorine bond changes more than the chlorine-chlorine bond, it means I've got more energy released on forming, therefore it's going to be more exothermic. Okay, let's just review what we've done. So first step, we went through the question, we understood we had to use a statement. We then started with drawing the electron configuration and linking the electron configuration to the statement. We then tried to apply it to the example we're given with the bonding. The only part of actual information I had to use was that bond breaking is when is endothermic and bond forming is exothermic. So that's the only real part. We had to know what this overall energy change is about. But that's about it. And so you just work step by step through this process. And it's a brilliant question because it doesn't use too much memory. However, it does require you really to understand everything that's going on here.